Imagine a spaceship, sleek and silver, hurtling through the vast emptiness of space. This vessel, a marvel of human engineering, is designed to withstand the most extreme conditions the universe can throw at it. As it glides through the cosmos, it passes by stars, planets and nebulae, each a testament to the vastness and beauty of the universe. The spaceship's mission is not just a journey through space, but a journey through time itself. Its destination, a black hole, an object of immense gravity lurking in the cosmic expanse. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape from them. They are formed when massive stars collapse under their own gravity, creating a point of infinite density known as a singularity. The spaceship's crew is on a mission to study this black hole, to understand its mysteries and unlock the secrets of the universe. As the ship draws closer, something strange begins to happen. Time itself starts to behave differently. The closer the spaceship gets to the black hole, the more pronounced these effects become. Clocks on board the ship tick more slowly compared to those on Earth. The crew experiences time at a different rate, a phenomenon known as time dilation. This effect is a direct consequence of the immense gravitational pull of the black hole. It slows down, stretches, and ultimately at the very edge of the black hole seems to freeze entirely. This boundary, known as the event horizon, marks the point of no return. Once crossed, nothing can escape the black hole's grasp. The event horizon is a place where the laws of physics as we know them cease to apply, and time itself appears to come to a standstill. This isn't science fiction, it's one of the mind-bending consequences of Einstein's theory of general relativity. According to this theory, massive objects like black holes warp the fabric of space-time, creating gravitational fields that affect the passage of time. The closer an object is to a massive source of gravity, the slower time passes for it. This effect has been confirmed by numerous experiments and observations, making it one of the most fascinating aspects of modern physics. Black holes, those enigmatic cosmic monsters, possess the power to warp the very fabric of space-time, creating regions where the familiar laws of physics break down. They bend light around them, creating a phenomenon known as gravitational lensing, where light from distant stars is bent and magnified by the black hole's gravity. This warping of space-time also creates tidal forces that can stretch and compress objects, a process known as spaghettification. Their immense gravity creates a cosmic whirlpool, trapping everything that ventures too close, even light itself. This gravitational pull is so strong that it can capture entire stars, ripping them apart and consuming their matter. The energy released in this process can create powerful jets of radiation that shoot out from the black hole's poles, visible across vast distances in the universe. Black holes are not just destructive forces, they are also engines of creation, shaping the cosmos in ways we are only beginning to understand. To understand how black holes affect time, we need to rethink our everyday understanding of gravity. Gravity isn't just a force pulling objects together, as we might have learned in school. It's much more complex and fascinating. Instead of a force pulling objects together, Einstein imagined gravity as the curvature of space-time. This revolutionary idea changed the way we perceive the universe. According to Einstein's theory of general relativity, massive objects like stars and planets bend the fabric of space-time around them. Imagine a bowling ball placed on a trampoline. The ball creates a dip, a curvature in the fabric. This analogy helps us visualize how massive objects like planets and stars warp the space-time around them. The more massive the object, the deeper the curvature. This is similar to how massive objects warp space-time. When a planet or a star bends space-time, it affects everything around it, including light and time itself. The warping of space-time is more pronounced near extremely massive objects like black holes. Now imagine a clock placed at the edge of this dip. Compared to a clock far away, the clock near the massive object runs slower. This phenomenon is known as gravitational time dilation. The closer the clock is to the massive object, the slower it ticks. This is time dilation. Time itself is affected by the curvature of space-time. The stronger the gravitational field, the more significant the time dilation. Near a black hole, where gravity is incredibly strong, time can slow down dramatically. The stronger the gravity, the slower time runs. This means that if you were to observe a clock near a black hole, it would appear to tick much more slowly compared to a clock far away from the black hole. This effect has been confirmed by experiments and observations, making it one of the most intriguing aspects of our universe. Imagine astronauts venturing close to a black hole. To them, time would seem to pass normally, but to an observer far away, the astronauts' movements and their clocks would appear to slow down. This is not just science fiction, it's a real consequence of the laws of physics as described by Einstein's theory of general relativity. The effect becomes even more extreme as you approach the event horizon of a black hole, the point beyond which nothing can escape. Time near the event horizon slows down so much that it almost comes to a standstill. This creates a fascinating and eerie boundary where the laws of physics as we know them start to break down. Black holes, with their immense gravitational pull, offer a unique laboratory for studying the nature of time and space. They challenge our understanding and push the boundaries of what we know about the universe. The interplay between gravity and time near these cosmic giants continues to be a subject of intense research and fascination. As we delve deeper into the mysteries of black holes and warped space-time, we uncover more about the fundamental nature of our universe. The relationship between gravity and time is a profound one, revealing the intricate and beautiful tapestry of the cosmos. The journey to understand these concepts is ongoing, and each discovery brings us closer to comprehending the true nature of reality. As we venture closer to a black hole, the curvature of space-time becomes increasingly extreme. The immense gravitational forces at play warp the very fabric of the universe, creating a region where the rules of physics as we know them begin to break down. This warping effect is so powerful that it bends light and distorts time, creating a surreal and almost incomprehensible environment. Eventually, we reach a point known as the event horizon. This boundary marks the edge of the black hole, a threshold beyond which escape is impossible. The event horizon is not a physical surface, but rather a conceptual boundary, a point of no return. This is the point of no return, a boundary in space-time beyond which nothing, not even light, can escape the black hole's gravitational pull. The gravitational forces here are so intense that they trap everything that crosses the event horizon, pulling it inexorably towards the singularity at the black hole's core. At the event horizon, time dilation reaches its most extreme point. Time itself seems to stretch and slow down under the influence of the black hole's gravity. For an observer far away, this effect is particularly striking. From the perspective of an observer far away, a clock falling into a black hole would appear to slow down infinitely as it approaches the event horizon, eventually freezing in time. This phenomenon occurs because the gravitational pull of the black hole warps space-time to such an extent that time itself is affected. The clock, however, would experience no such effect, plunging relentlessly towards the singularity at the heart of the black hole. To the clock, time would continue to tick normally even as it is drawn into the black hole's depths. This stark contrast between the experiences of the distant observer and the falling clock highlights the mind-bending nature of black holes and the extreme conditions that exist at their event horizons. For any object or spacecraft attempting to navigate near the event horizon, the experience would be equally harrowing. The gravitational forces would stretch and compress the object in a process known as spaghettification. This extreme tidal force would elongate the object along the direction of the gravitational pull while compressing it along the other directions, ultimately tearing it apart. Spaghettification is a vivid demonstration of the immense power of black holes. It serves as a stark reminder of the dangers that lie at the edge of these cosmic giants. Despite the peril, the study of black holes and their event horizons continues to captivate scientists and astronomers, offering profound insights into the nature of the universe and the fundamental laws that govern it. Through advanced telescopes and simulations, researchers strive to unlock the mysteries of black holes, seeking to understand their formation, behavior, and impact on the cosmos. Each discovery brings us closer to comprehending these enigmatic objects and the role they play in the grand tapestry of the universe. The event horizon, with its profound implications for space and time, remains one of the most fascinating and challenging frontiers in astrophysics. As we continue to explore and learn, we are reminded of the boundless wonders and mysteries that the universe holds, waiting to be discovered. Section 4, Einstein's universe, gravity's dance. Einstein's theory of general relativity revolutionized our understanding of gravity and its relationship to space and time. It painted a picture of a dynamic universe where massive objects warp the fabric of space-time, influencing the motion of objects around them. Imagine two celestial dancers locked in a cosmic waltz. The more massive dancer leads, their movements dictating the steps of their partner. Similarly, massive objects like stars and black holes dictate the curvature of space-time, influencing the paths of planets, stars, and even light itself. Section 5, Black Hole Pioneers, from theory to observation. The concept of black holes emerged from Einstein's equations long before we had the technology to observe them directly. Physicists like Carl Schwarzschild and Subramanian Chandrasekhar made groundbreaking contributions to our understanding of these enigmatic objects. Schwarzschild, while serving in the German army during World War I, found a solution to Einstein's equations that described the space-time around a spherical, non-rotating mass. This solution, now known as the Schwarzschild metric, was crucial in understanding the properties of black holes, including the existence of the event horizon,